Connectivity. So we will study how a given graph is connected. So we will give it some formal definition. We will say that a graph is connected if we can travel from any vertex to any other vertex following the paths given by edges. If we can do that, then we will say the graph is connected. So I said a path. What a path mean here? So informally, the path is a sequence of edges inside the graph, so going over these edges. And the formal definition of path is the following. Okay. So a path of length n. A path of length n from a vertex u to a vertex v is a sequence of n edges. So this is the length n of n edges. We call this sequence of edges e1, e2, all the way to en of g, for which there exists a sequence of vertices. So in here, u is x naught and v is xn, and the vertices in between are called x1, x2, all the way to xn minus 1, such that the edge ei has endpoints xi minus 1 and xi. So let me make it clear. For instance, if we start our 2, then we move to a vertex, we call u x0. Move to another vertex, the next vertex after that, in our path, we will call it x1. The next vertex, we will call it x2, and so on. And say this is x3, and say this is x4, which is the terminal point that we will call it v. In here, n is 4. We have 4 edges. So we will say this is the length path. This is a path of length 4. It is a path from u, from vertex u to vertex v. And now what about the edges? We call this edge to be, so we started at e1. This is e1, this edge is e1, this edge is e2. So e2 connects between x1 and x2, and e1 connects between x0 and x1, and this is e3, and this is e4. Okay, so simply this is a path, a very intuitive definition. When the graph is simple, we denote this path by the vertices. So it is enough to tell the vertices. If we make a list of vertices in our path above, we will say, okay, it is x naught, x1, x2, x3, x4. When we see such a list of vertices, that means we are traveling from one to the next one, to the other. And now we are assuming the graph is simple, so there is no confusion which edge I follow from one vertex to the other, because there is only one vertex, one edge going between any two consecutive vertices in the list. So stating two vertices directly means the edge between them without confusion, because every edge is uniquely determined by the vertices that are at the endpoints of that edge whenever the graph is simple. Okay, now a circuit, a path is called a circuit if it begins at ends and ends at the same vertex. Okay, so if I want to demonstrate that, so it goes like this. It keeps going inside the graph somehow, and then it comes back to here. So this is x naught, x1, x2, x3, x4, and x5. And this is a circuit. A path of the circuit passes, we will say, passes through the vertices, and it traverses along the edges. Okay? So simple definitions for a path and a circuit. Remember, a circuit is a path, but it starts at the same at some vertex, and it comes back, it follows some path, closed path, and comes back to the same vertex that you started with. So at the end, a path or a circuit is simple if it does not contain same edge more than once, if it does not comes back from an edge that it used to go in one direction, okay, in some direction. Okay, so let's make it clear by following some example. We will say that this list here, A, B, C, D, E, where is A? Okay, here is A, then we go to B, we go to C, and then we go A, B, C, A, sorry, we go A, D, no, this is D, not A, so I will take this away. We start with A, so I mean now I'm drawing this path with this color. I'm going to D, and then going to, where's C? Oops, C is there, and then I go to C here, and then I go to F, it is here, then I go to E. Okay, this is a path. Let's make another path, which is a circuit. We start at B, and then go to C. Oops, C is there. Start at B, go to C, and then where? To F. Okay, and then E, okay, and then B, we came back to B, so this is a circuit. Okay, so let's see what we have more. We have the path A, B, D. Okay, let's follow that again with, I will use red. It is A, B, E, so A, B, E, D, A again, and then B. So we're going 2 times over the edge AB. Is not simple, so it says that this path is not simple. It contains the edge AB more than once. Okay, so we have seen what is a path, what is a circuit, and what is a simple path or simple circuit. Now we want to use that to define connectedness inside an indirected graph. Okay, so let's see. An indirected graph is called connected. If there is a path between every pair of distinct vertices in the graph. If there is a path between every pair of distinct vertices of the graph. If we can travel from any vertex to any other vertex following traversing the edges, then we say it is connected. And it is not connected. If it is not connected, we say it is disconnected. That means not connected. That means there is 2 vertices that I cannot travel from one to the other, and there will be kind of isolation. We will see the graphs above down there actually tells us the idea. We say that we disconnect a graph when we remove a vertex or edge or path to produce a disconnected graph. We will be interested mainly here in connected graph. Will not be very interested in disconnecting graphs. Let's see. Okay, example. The graph G1 is connected. Okay, you can see that in this graph here, we can travel from any vertex to any other vertex following the edges. No problem. We can go from anywhere to anywhere. But this graph here is not connected. Simply, I cannot go from C to D, or from B to D, or from A to E. There are many vertices that I cannot go from one to the other. And you can see it is disconnected. It has 2 parts, 2 isolated parts. So this is the idea. Okay, now what's about connected components? Whenever I have a graph which is connected, then it is one piece. So it has one connected component. When I have a graph which is not connected, the one we see to the right, it has 2 connected components. So we will define that. A connected component of a graph G is connected subgraph of G. That is a proper subgraph of another connected subgraph. So it means, for instance, this is a connected component. Okay, this is another connected component. Okay, now what it says here, that is not a proper subgraph of another connected graph of G. So connected component of a graph is a connected subgraph that is not a proper subgraph of another connected component that is not a proper subgraph. So again, look at this in here. This is a connected component, right? Connected subgraph. Now, one of you may think, well, okay, I want to take this part from here. I want to take this part like E, F, and D. And I will say that it is connected component. And this is, no, this is not a connected component of G. Why? Because it is a proper subgraph of another connected graph. The green in there, the bigger one, is a connected subgraph, right? The one in red is a subgraph of that connected graph. And it says it shall not be a proper subgraph of another connected subgraph. So we will not take the red here as connected components. So connected components are subgraphs that are connected. Okay? But they are not coming from another bigger subgraph which is connected. They are not coming this way. Okay. Okay, here it make it clear. So let me drag this down. Again, the second sentence here make it clear. It says that is a connected component of a graph G is a maximal connected subgraph of G. Is a maximal connected subgraph of G. You notice that? So the red here is not maximal connected. It is connected part, yes, but it is not a connected component. It is not a connected component because it is not a maximal connected subgraph, because the green one in here is a connected subgraph that contains the red one. So we will not take the red one as connected component. It is connected subgraph, yes, but it is not a connected component of G. Okay. The graph H is a union of three disjoint subgraphs. Okay, if we have the graph H, which is given that way, so you can see these are the connected components. H1, H2, and H3 are connected components. Again, we will not take this part here as connected components. No, because it is contained in a bigger subgraph which is connected. Now we will see connectedness in directed graphs. We have already seen connectedness in undirected graphs. Now we will see in directed graphs. So definition: a directed graph is strongly connected if there is a path from A to B and from B to A, wherever A and B are vertices in the graph. Okay, strongly connected. If I can go from A to B and then I can come back. Remember, directed graphs may have some edges going in one direction but not coming back in the opposite direction. So we will say it is strongly connected if we can go from one vertex to another and then come back, maybe following the same vertices if the graph allows me, or following some other vertices whose direction allows me to come back from B to A. Okay, we will see. Another definition which talks about weakly connected. A directed graph is called weakly connected if there is a path between every two vertices in the underlying directed graph. So what does that mean? If I have a directed graph, if it is strongly connected, then we are done. It is then weakly connected. But what if I have a directed graph which is not strongly connected, which means there is a vertex A and B, I can go from A to B, but I cannot come back. Now, we will take this graph without directions. So take the same graph, but remove the direction. That's what we mean in the underlying undirected graph. So take off the direction from the graph and keep the edges. Okay? Now we get an undirected graph. If that graph is connected according to what we have already learned, then we will say that directed graph is weakly connected. So again, if we have a graph which is not strongly connected, a directed graph which is not strongly connected, what we do? We take off the directions and keep the edges. So we get an undirected graph. We investigate the connectedness of this undirected graph. If we find it connected, then we go back to the original graph with direction and say that directed graph is weakly connected. So it is not strongly connected, but its underlying undirected graph is connected. So we will say the directed graph is weakly connected. Okay, here we go. So to make that clear, for sure we need to see the following example. G here is strongly connected, and every strongly connected graph is also weakly connected. So let's check it out, which means G is strongly connected. That means I can go from any vertex to the other and then coming back. Let me see if I can go from A to D. This way takes me from A to D. Fine. Can I go back from D to A? Yes. This way takes me from D to A. Okay. Let's try with another color, green. From A to C, I can go this way from A to C. I can come back this way from A to C. Okay, from B to E, I can go this way from B to E, and then I can come back this way. So try that between any two vertices. You can go from one to the other and come back some other way using some other edges. Okay, now here H is not strongly connected. That means there is two vertices. I can go from one to the other, but I cannot come back. Let's look for them. What are they? Look in here. A has one edges. No edges are coming out from A, but there are no edges coming out. All edges are coming in A, and same thing for D. All edges are coming out of D. No edges is coming in. So, okay, so I can go from D to A. Okay, but I cannot come back. There is no way to come back from here. It is, or this is says B. This is another example. I can go from no direct path from A to B. So I can, okay, so this is easier there. I can go from B to A, but I cannot come back from A to B. Or I can go from D to A, but I cannot go back from A to D. There are no edges that allows me. Okay, so this is not strongly connected. So is it weakly connected? So let me take off the colors from the graph H. So is it weakly connected? That means if we take these directions away. So let me use some color to take the directions away. So if we take these directions away, so we get the underlined, okay, underlined undirected graph. So is it connected? Remember, for an undirected graph, it is called connected if I can go from any vertex to any other vertex. Directions here are not forced. We are not forced to use directions of edges. We can go from anywhere to anywhere, from one direction to other, or any edges. So it is connected. So so let me write it here. The underlined undirected graph of H is connected. Okay, that gives us H is weakly connected because it is not strongly connected, and the underlying graph is connected. So okay, I believe now ideas are clear. And it adds one more thing, that the graph H has three strongly connected components. The subgraph consisting of the vertices B, C, and D. Oh, okay, so I need to bring back if we want to talk about this, I need to bring back that direction, so I need to erase all that. Okay, now if we take, it says BC and D here. Okay, so this one graph is strongly connected components. We have talking about already the connected components above there. Now we are talking about strongly connected components. So be aware that when we deal with directed graphs, we will add strongly connected. So when we talk about strongly connected, then we are considering directions of edges. So let's look for the strongly connected component of H. If we look back at H without directions, then it is connected. Then we will not talk about connected component of H. We will not talk about connected component of H because H is connected as an undirected graph. But as a directed graph, H is not strongly connected. So we will look for strongly connected components of H. The very first one is that contains the vertices B, C, and D, and it is in green in here. That means in this green part of the graph, I can go back, can go from any vertex to the other and then come back. Like we can go from B to C and C to B. That's clear. Or from D to C and come back from C to D. Okay. So the strongly connected subgraphs are this one here, and the edges BC itself, CD, and DB, just edges. This BC in here. So it says BC. No? Okay, sorry. I misunderstood. I mean this whole green that contains the vertices and the edges. The vertices and the edges between them. I thought the edges themselves are strongly connected components. Okay, so this is the very first connected component. The second one is just the vertex A. The vertex A is another strongly connected component, and another one is just the vertex E, another strongly connected components. Okay, these ones are very trivial. Okay. Good, so now we learned about paths and connectedness. We will see some relations between path and isomorphism. Remember in the last lecture, we learned about how the two graphs are isomorphic, or how we find they are not isomorphic. Remember, if they have different number of vertices, then they are not isomorphic. If they have different number of edges, then they are not isomorphic. If we have some edge in one of the graphs whose degree is some number, but we don't have if we have some vertex in one graph with a certain degree, but the other graph does not have a vertex of that degree, then these two graphs are not isomorphic. More general, if we have a number of vertices with certain degree, and we don't have the same number of vertices in the other graph with that certain degree, then they are not isomorphic. Okay, so in general, again, the number of vertices with a certain degree in some graph must be equal to the number of vertices to the in the other graph who has the same degree, who has the same certain degree. This does not necessarily mean the two graphs are isomorphic, but if we find such a difference a certain difference, then they are not isomorphic. Okay. Now here we will use the path to help us to decide whether two graphs are isomorphic or are not. Okay, so let's see how is that does that help. In here it says that the existence of a simple circuit, for example, of a particular length, is useful invariant that can be used to show that two graphs are not isomorphic, which means that if I have two graphs and I found a circuit in one of them of certain length, but I could not find a circuit in the other with that length, then those two graphs are not isomorphic. So we have one more information. Okay, so let's apply this in the following example. Determine whether these two graphs are isomorphic or no. Now if we go to the three invariants in here, we will find that they have the same number of edges, they have the same number of vertices and then of edges, and the degrees of the vertices. So all agree, the graphs agree on the two graphs agree on all of that. So if you go, graph G has 4 vertices, each one of them has degree 3, and same thing for graph H. Also, graph G has 2 vertices, each of them is of degree 2, they are U1 and U4 here, and the graph H has the same thing, 2 vertices of degree 2 that are V1 and V4, and same number of edges and degrees and same number of vertices. Okay, so we don't know whether they are isomorphic or no, and in this example taking circuits will help us to decide. Okay, so let's see what this says. Both G and H have 6 vertices and 8 edges number, okay, and has 4 vertices of degree. This is what I just talked about. Okay, so let's see what other observation we might have about these two graphs. However, H has a simple circuit of length 3. Let's look for it. Simple circuit of, so we can go, okay, there are 2 of them, V4, V3, V1, V4. So the simple circuit for H here, we can say it is V4, V3 and V5, and then we come back to V4. As we learned, list of vertices tells us this is a path, and it starts at V4, ends and V4. That means it is a circuit. Okay, so this list represents a circuit of length 3, but we cannot find the circuit of length 3. G has no simple circuit of length 3. If we go travel from any vertex and come back to that vertex in G, we will not find a way or a path or a circuit of length 3, simple circuit. There is no such one, so they are not isomorphic. So that means G and H are not isomorphic. Okay, let's see what this example says. We also use paths to find mapping that are potential isomorphism. Okay, so we might think or expect two graphs, or seems to us that two graphs are isomorphic. And remember what we have seen in the last lecture, how we matched the vertices from one graph to the other. We did some effort. Now we can use path to lead us to define such isomorphism. Now, before we start showing they are isomorphic, we must make sure they agree, all agree for the two graphs, the number of vertices, edges, and degrees of vertices. Check it out, they are all equal. Okay, now both graphs have simple circuit of length 3, and simple circuit of length 4, and simple circuit of length 5. Where are they? Of length 5, for example, we go from, in H we go from V1 to V5, v4, v3, v2, and comes back to v1, or the opposite way. Can I find a simple path of length 5 in G? We go to U3, from U1 to U5, U2, U3, U4, and U5. This is a simple path. Okay, good. So look for the simple paths of length 4 and length 3. Okay, so let me remove all that. Okay, okay. So let me go down and see. Okay, now in here, the ones I just marked, this is a path in G. It is of length 1, 2, 3, 4, right? U1, U4. So let me remove these things from the graph here. And let me mark this path in G in blue. U1 to U4. Here, U1, U4, U3, U2, U5, and then come back to U1. So, okay. And now, the path of length 4, that's length 4, yes, length 4, in H starts at V3 to V2, V1, V5, and V4. Okay, so what we do now, these two paths shall lead us to match the vertices. So the first path in G started at U1, but the path in H started at V3. So that leads me that I want to make the image of U1 to be V3. The second vertex in the path in G was U4, but the second vertex in the path in H was V2. So I will think to send U4 to V2. And similarly, we do for the other vertices, and looks to us that the isomorphism will send each one of these vertices to its corresponding vertices according to the order in both paths. Here we go. It says now f of u1 goes to v3, f of u4 to v2, and so on. Now it will lift to you that it is to show that f is an isomorphism. It is a one-to-one and onto map. So what we need to show that f preserve edges. How we show that they are f preserve edges? We go back to the edges and see, for example, the edge connecting U1 and U4. Okay, if they are connected by some edge, then f of U1 and f of U4 must be connected also. Okay, and we do that for every pair of vertices. Okay, and I will leave that to you. Or also there is another way, as we have already the list of vertices in here in H, in G, to be U1, U4, U3, U2, U5. So make the adjacency matrix of G according to this order of vertices, and then again make the adjacency matrix of H according to this order of vertices, V3, V2, V1, V5, and then you must find out that the two matrices you have computed are the same, and that shows F and G are isomorphic.